In this module, we have seen that starting with Newton's second law, which is sigma F equal to ma, also written as d over dt of m times v, or d over dt of linear momentum, in a Newtonian or inertial reference frame, we could get a couple of relationships. So we could say that some of the forces acting on a particle is equal to rate of change of linear momentum, in short we write it as p dot. And if we took dt on the left hand side and integrated it, we got change in linear momentum, right? And we said that if some of the external forces on a particle is zero, then linear momentum is always conserved. And this could be true for a system of particles as well. There is another concept analogous to the concept of linear momentum called angular momentum. So if we have a particle, so the particle P traveling along some path, okay, and we pick a reference point Q. Okay, now the reference point Q could be any point in the space. This could be a point which could be fixed. This could be a point which is actually moving. And the velocity of the particle P is given as Vp. Then we can define a concept called H sub Q, called angular momentum. Angular momentum as moment of momentum. Now pay attention to that. So moment of momentum, what would that quantity would be? So moment of a force is defined as r cross f. Moment of momentum is defined as r, the position vector, of particle P with respect to Q cross m times the mass of the particle times the velocity of the particle, right? So this definition, as you can see, is analogous to the definition of moment of a force. So moment of a force, if you were taking, is defined as r cross f, right? So this indicates a moment, and that's the force. This is the moment of momentum, that's the moment part, and this is the linear momentum part, right? When we say moment of momentum, the word momentum actually refers to linear momentum. So this is how we define the angular momentum of a particle. So angular momentum is Rp with respect to Q, that's this position vector. Notice how I picked a different origin for the reference frame. It is not necessarily Q. It could be, but it doesn't have to be. Okay, so that's how we define the angular momentum. Now the question is, can we relate this angular momentum quantity to something else, just as we were able to relate the change in linear momentum to linear impulse of a force, integral sigma f dt? The question is it possible to relate the angular momentum to something? Okay, so yes, the answer to that question is yes, we can do that. But first, let's look at a simple example of how we compute the angular momentum. So let's say I have, an aircraft. Okay, aircraft is moving with some velocity v0, horizontally in the up in the sky, right? And at any instant, let's say this aeroplane is right over here, okay, right above. So this is, x-axis is y-axis, this is z-axis, and it is a distance r away from the origin of this reference frame, okay? And at this instant, this velocity is given as v0, and we want to know what is this angular momentum. Now, notice how this particle, this plane, is actually not moving along a curved path. It's moving along a straight line. That doesn't mean its angular momentum is zero. Okay, so angular momentum of a particle is not going to be zero just because the particle is moving along a straight line. So in this case, we are interested in angular momentum about point O, and that is equal to r, the position vector of the particle at this instant, cross m times its velocity. So r is r k hat, and velocity is v0 I hat. So this gives you r times m v0, and k cross I is equal to j hat. So that is the direction of angular momentum, right? So this is how we define the angular momentum of a particle. All you have to do is do r cross mv, and it'll give you the angular momentum. Now let's come back to our original problem. Okay, so the original problem is that we have the angular momentum defined over here. We want to know what it relates to, right? Maybe the forces, maybe the moment, or something like that. So let's take its derivative. So h sub q is equal to r of p with respect to q cross m times vp. Okay, so if we take the derivative, we get r dot p with respect to q cross mvp plus r of p with respect to q cross m v dot p. Okay. All right. So what is r dot p with respect to q? That's velocity of p with respect to q cross mvp plus r of p with respect to q cross m times v dot p is nothing but acceleration of point p, right? Okay. So this is vp minus vq cross mvp plus r of p with respect to q cross, what is this quantity? M times acceleration. M times acceleration of a particle is defined as sigma f equal to ma, right? So we know this. Sigma f is equal to mass times acceleration of particle p. So we can write this as simply sigma f, right? Sum of all the forces acting on the particle. Okay, so we have vp cross mvp, which would be 0. So we have minus vq cross mvp plus this quantity r of p with the q cross sigma f. What is that quantity? So that is, let me draw this again over here, the figure. So here is our particle p moving with velocity vp, tangent to the path. Here is point q, which is a reference point, and that's the position vector of p with respect to q. So r of p with the q cross sigma f is nothing but the moment of all the forces acting on p with respect to q, right? So we'll write this as simply sigma mq to indicate this is sum total of the moment of all the forces acting on p with respect to q. So I'm going to take this negative quantity on the left hand side and I will write it like this. So I'll write sigma mq first, and this is equal to h dot q plus vq cross mvp. Okay, so that's the relationship we have now for the rate of change of angular momentum. And this is fairly similar to what we had before when we related the rate of change of linear momentum with some of the external forces, which was right over here, this, right? So let me write this again. So we have also sigma f equal to p dot, where sigma f is some of the external forces and p dot is rate of change of linear momentum. While this equation is saying that sum of the moment about a chosen point q is equal to rate of change of angular momentum plus velocity of the point q itself cross m times vp. So in this case, this is general case, the point q could itself be actually moving. So for example, you could have an aircraft and you could have another aircraft, and the two aircrafts were tracking each other, and the one that was tracking, let's say the other one, was attached to the point q. Okay, so q had some velocity because that one is moving, and p has some velocity, and you were trying to compute the angular momentum, rate of change of angular momentum, and relating it with the total moment acting on the particle p with respect to q. You could write this relationship. So let's look at some of the special cases. Case 1 is when q is a fixed point. So when q is a fixed point, that means velocity of q is 0, right? When velocity of q is 0, then this relationship simplifies to sigma mq equal to h dot q, right? And that is very, very similar to, this relationship over here, right? It's very easy to remember. So sum of the force is equal to rate of change of linear momentum, and you can also say that sum of the moment about point q is equal to rate of change of angular momentum about the same point, right? But this is true only when q is a fixed point, right? Another case would be when, let's look at here, q and p are parallel to each other. So when vq is parallel to vp, then also vq minus vq cross mvp would be 0. Even in that case, we will obtain the same relationship, which is that sigma mq is equal to h dot q, right? So we get the same relationship as we get over here. And of course, we will also have the trivial case when vp is 0, which means that the p is stationary, then also sigma mq would be equal to h dot q, right? But that's not an important case because that will be trivially true, okay? So we get this, nice relationship, and we will pretty soon see how we can use this. In fact, this particular relationship that we have obtained is something that we would need crucially for analyzing the motion of the rigid bodies, which cannot be seen as a system of particles, but they're more like, continuous medium, right? There are infinite number of particles in there, but it is really not modeled as a system of particles. But a similar relationship would be derived for doing the kinetic analysis of rigid bodies, either in a plane or in a space. So just as we have done before, we have derived these kinds of relationships for individual particles. We also want to see what happens when you have a system of particles. Okay, so let's do this for a system of particles. So system of particles. So system of particles by definition is a system, and again we are going to be only looking at the closed systems where the mass of the system is really not changing, right? So you have a large number of particles, all right, and you will choose a reference point Q. You still have O over here, all right, and you can write that we have angular momentum of individual particle, let's call it HI, as Ri cross m times velocity of the particle I, right? So if this is particle Pi has a velocity Vi, then you have this as your position vector, okay? That's your position vector, and you're doing a cross product between this position vector with the linear momentum of the particle. So let me say this is Mi because we're looking at individual particle I. So if I want to get the angular momentum of the system, I have to add these all together. So we have to write this for individual particles and we have to add them together. So we get sigma Ri cross Mi Vi. So just as we have done before, we will take the derivative of this equation. So let's see what we get. So H dot system is equal to going to be sigma R dot I cross Mi Vi plus sigma Ri cross derivative of the second term. Okay, so what is this? This is sigma R dot I is the velocity of the particle Pi with respect to Q. So this would be sigma Vi minus Vq cross Mi Vi plus sigma Ri cross, and this is nothing but the acceleration, so that's actually Mi times acceleration of particle I. So what do we get? Vi cross Vi cancels, so we get minus, and Vq is not part of the indices, so we can take Vq outside, so this becomes minus Vq cross sigma Mi Vi plus sigma Ri cross Mi Ai. What is that? So we know that Mi Ai is nothing but the sum of all the external forces plus all the internal forces, right? So Mi Ai is nothing but the total forces acting on the particle Pi. So if you look at the free body of the particle Pi alone, this is Pi. Let's say all the external forces on Pi are represented by Fi. So this is not to say there's only one external force. Whatever number of external forces you have, you add them together vectorially and you get one vector, which is Fi. And then you have a bunch of internal forces, right? So Fi1, Fi2, Fi3, and so on, right? So you have a bunch of these forces. So that's what we have over here, okay? Now, if you add all the internal forces together for the system, we've already seen that they cancel out, right? Because they occur pairwise, equal in magnitude, opposite in direction. But now, this is not just a summation of the forces. What we have over here is actually a cross product, right? So let's look at this term by itself, and we'll come back to this over here. So this is essentially Ri cross Fi plus sigma Fij, right? This is basically for just one particle, right? And this summation indicates it has to be done for all of the particles, right? Okay, so if we do this, this is the sum total. This is the total moment about point Q over here, right? Then we want to see if the effect of internal forces cancels out or not, right? So this can be written as this last term can be seen as sigma Ri cross Fi plus Ri, again, we will repeat the sigma over here, cross sigma Fij, right? So this is double summation over here. Okay, so let's just look at, two forces. Let's say we have, F12 and we have F21, right? This is particle 1, this is particle 2, and F12 is actually equal to minus F21, okay? And R1 is the position of particle 1 and r2 is the position of particle 2, and that's our reference point Q. Okay, so if we can make an argument that the moment of inertial forces pairwise cancel out, then we know we can do that for all the particles, right? So what is this quantity? So this quantity for two forces would be R1 cross F12 plus R2 cross F21, right? This is just for these two forces. So this is R1 cross F12 minus R2 cross F12, because F21 is equal to minus F12. So this is actually R1 minus R2 cross F12. Now let's look at this term. Does this term equate to 0? It turns out it does actually, because F12 is acting along this direction, right? That's the direction F12 is acting. And R1 minus R2 is this difference vector, which will be also obtained along this direction, right? This is R1, this is R2. So the difference is basically nothing but the vector joining P1 and P2. So both of them are always going to be pointing in the same direction. And that means that this quantity is nothing but 0, right? So we can see that the internal forces, if you compute their moment and you add them together, they also occur, pairwise, and they all cancel out because of this reason, right? Which means that when we compute the moment over here, the internal forces will not play any role, right? Which means that this last quantity over here would become the moment of all the external forces acting on the system with respect to our chosen reference point Q, right? So that's the simplification we are achieving. So let's write this quantity. This is now nothing but sigma m about Q. Let's write that. So sigma m about Q is equal to h dot of the system plus VQ cross this first term, which is sigma mi vi. Let me first write that and then I'll simplify that. Sigma mi vi. Now what is sigma mi vi really? Okay, so to understand this, we'll look at the concept of center of mass. Okay, so we're taking sort of a detour over here now. The concept of center of mass. So for a system of particles where you have lots of particles in here, you can find the center of mass, let's say point G, and this is the position vector Rg as m times Rg, where m is the sum total of all the mass of the particle, equal to sigma mi Ri. Right? So yeah, this is particle Pi, that's the position vector Ri. There is particle Pj, that's the position vector Rj. So you multiply the mass of each particle with its position vector with respect to your origin of reference frame, and that would be equal to the total mass. So m is equal to sigma mi times the position vector. So position vector is obtained by this equation, and this is something that you may have seen in your physics classes as well. Okay, now what can we do with this? We can differentiate it once, and what do we get? We get m times velocity of center of mass equal to sigma mi vi, right? So what this is saying is that if you know the velocity of individual particles and you know their masses, you multiply them, you add them together vectorially, and then you divide by the total mass of the system, and you'll get the velocity of center of mass, right? If you differentiate it once more, you get m times acceleration of center of mass equal to sigma mi ai, right? So these two relationships are additional relationships that we will use from this point onward. So sigma mi vi is something that we have here, right? So that is equal to m times vg. So let's substitute that. We get sigma mq equal to h dot of the system plus velocity of q cross m times vg. Why? Because m times vg is equal to sigma mi vi. That is what we need over here. Okay, so that is the expression for a system of particles, right? And this isn't anything different from really what we have seen before, except that now we're doing it for a system, right? So this is for one particle. This is one particle. So one particle, the relationship was the sum of the moment of the forces about point Q is equal to rate of change of angular momentum about Q plus VQ cross MVP. Now, in our system of particle, we have the sum of the moment of all the external forces acting on the system equal to h dot of the system plus VQ, which is same, cross, instead of MVP, now we have MVG, which is the velocity of center of mass, right? So once we have this, again, we can talk about some special cases. So special case would be, let's say case 1 is when q is a fixed point. Q is a fixed point. That implies velocity of q is 0, and in that case sigma mq is equal to h dot of system, right? Again, case 2, just as with the particle, is that q is a vg is, let's say g is a fixed point. So in this case now we're saying g is a fixed point. So center of mass is a fixed point. Like if you take a system of particle and you constrain it about this point, let's say this is rotating about it, right? Just about center of mass. That means velocity of g is 0. So velocity of g is 0. Okay. So velocity of z is 0. Then also we get sigma and q equal to h dot of system. And of course we also have the trivial case where, velocity of q, well, it's not a trivial case, velocity of q is parallel to velocity of g, and then also you get the same relationship. So case 3 is vq is parallel to vg, and then also you get sigma mq equal to h dot of system. So now from this relationship, what is emerging is a principle or a statement of conservation of angular momentum. Just as we had conservation of linear momentum in the absence of an external force, now one can say that if there are no external moments acting on a particle, which means that if you take the moment of all the external forces acting on a system or on a particle, and if that is equal to 0, then h dot of the system is 0 as well. And if h dot is 0, which is the rate of change of angular momentum, then h should be constant, right? So if sigma mq is equal to 0, that means h dot q is 0, and that means h about q is constant, right? And this is called principle of conservation of angular momentum, right? Now, if this is actually not equal to 0, if let's say sigma mq is not equal to 0, then what do you get? So we've seen that sigma mq is equal to d over dt of hq. And remember, this is valid for both the system as well as particle. And of course, we are writing for simplification this equation for the case when this term, the second term, actually drops out, because either q is a fixed point or g is a fixed point, or the velocity of the point q and g are parallel to each other. So if that's the case, then we have this, and just as we had done before with the linear momentum and impulse principle, we can take dt on the left hand side and integrate this. This becomes integral dhq, which becomes change in angular momentum. And on the left hand side, we have this quantity similar to sigma f dt integrated over time, sigma mq dt, which is called, and you can probably guess this, angular impulse. You will recall that linear impulse was defined as integral sigma f dt, right, over from sometimes 0 to t, right? Similarly, sigma mq dt is defined as angular impulse, and this on the right hand side is the change in angular momentum, right? So this is change in angular momentum. So what it's saying is that angular impulse is integrated over time is actually equal to change in angular momentum, just as the linear impulse integrated over time was defined as change in linear momentum. So what can we use this for, right? So a couple of interesting examples that spring to mind right away are the examples where we have moment 0, and that typically happens when you have central forces. So central forces are forces where their line of action, their direction is actually pointing towards a reference point, maybe the origin of a reference plane, and in that case you can readily conclude that the moment of those forces would be 0. Okay, so that happens for a figure skater, who's trying to dance and trying to control her spin rate by extending the arms out or inward, or with the motion of satellites around a planet. Okay, so let's look at the example of figure skater, okay, because that's a simple one. So example, so we have a figure skater, okay. So what does a figure skater do? So, let me try to draw this. So we have, hands, we have the legs, okay, and you can extend the hands, you can bring them inward, right? So you can do that. So you bring them inward, and you can control the spin rate as when you do that. So essentially, when you do that, when you extend your arms inward and outward, you are basically changing the mass distribution around an axis about which you may be spinning, right? So let's say this is the axis about which you're spinning, and you're essentially changing your mass distribution, and that it has an effect over at the rate at which you are spinning about this axis, right? So assuming that there are no external forces acting on this person, the only external forces, of course, are the normal reaction from the ground and the mg, which actually go through the reference frame, which is attached right on this line. So if let's say this is the particle, we're modeling it as a particle, and you have this is your reference frame, okay, then n and mg are actually going through this point, right? And that means that there are no external forces acting on this person, right? Well, there are external forces acting, but there is no external moment. So sigma m, let's say this point is O, is actually equal to 0, right? Now, how would we take care of the mass distribution? Well, the mass distribution now means that we cannot treat this person as a particle anymore, right? So how should we model it? So one convenient way of looking at this is to say, let's say we have a tabletop, right, with a hole cut right in the middle, right? And we have a string that goes through this hole, right, and comes up, and then it's on the table, and there is a little disc attached to it, right? And this disc is basically allowed to rotate, with this as the axis of rotation, right? And you can pull this string down, and when you do that, essentially this disc, I should have drawn it like an oval actually. And when you pull this down, of course, it could get into this position because they pull the string down, which means that the distance from origin, let's say this is O, to here R, is changing, right? So when you pull the string down, you're changing the distance between the point O and the disc itself. All right. So you're changing basically the distribution of the mass about the axis of rotation, right? So now the question is, can we find a relationship between the spin rate and the distance from the origin? Okay. So if this is the case, then the only force acting on this disc is really the tension, right? If you draw the free body diagram of the disc, the only force is the tension. Of course, you have the normal reaction in mg, okay, but they balance each other out. So their moments would also be 0 about point O. And the moment of tension T would also be 0 because tension T is actually pointing along the radial direction, right? So which means that R cross T is 0, okay? And that means some of the moment about point O is 0 as well. So if some of the moment is actually 0, then we know from this principle that there will be no change in angular momentum, right? Because sigma m is 0. So if that's the case, we can say that h about O is constant. So just as we were able to apply principle of conservation of linear momentum in the absence of an external force, now we can say there are no external moments acting on this particle, and that means that angular momentum would be conserved as well. Now, what is the definition of angular momentum? Definition of angular momentum is R cross mv, right? So R is this position vector, so we'll write that R UR hat. So I'm going to pick UR hat to be my radial direction. And then of course I also have U theta hat, which is perpendicular to this, okay? So R UR hat cross M times velocity, and velocity of this in R theta system is R dot ER hat. So I'm using a notation here slightly. So I should either use UR hat or ER hat. So I'm going to just do ER hat. So the habit of doing that, R dot ER hat plus R theta dot E theta hat, right? Okay. So this is MR. Let's do the cross product. ER cross is 0. So we have only ER cross E theta. ER cross E theta is a vector perpendicular to this plane, right? So if this is ER hat and this is E theta hat, then there's a perpendicular, right? Let's call this K hat. Okay, so this would be R theta dot K hat. So we get MR square theta dot K hat. So that's your angular momentum. So notice how angular momentum is perpendicular to this plane, right? So radial vector, velocity vector. This is a cross product, so it's a vector that's actually pointing along the spin axis, right? In this case, MR square theta dot K hat. So MR square theta dot is constant, right? So MR square theta dot is constant. K does not change, it's constant anyway. So mass doesn't change. That means r square theta dot is constant, right? So this is telling you that if you know initial position, initial angular rate, that would be equal to, let's say final R2 and final theta dot, right? So this is theta dot 2. I flip this. So this is theta dot 2. So theta dot 2 is equal to R1 square over R2 square times theta 1 dot, right? So which means that if let's say the R2 is less than R1, then theta dot is going to be more. And this is exactly how a figure skater would control the rate of a spin, by extending the arms inward or outward. When she extends her arms outward, then R is larger. That means theta dot would be smaller. And a similar example can be seen for motion of a satellite around a planet. So let's say we have our beloved planet Earth, and we have a satellite that can go around it. Okay, so we have the points which are called perigee as well as apogee, and these are the points nearest and farthest from the Earth. It may look like as if the Earth is right in the center of the orbit of the satellite, but it doesn't have to be that way. In fact, right, this distance, let's say this is RP, and this is the distance RA. Of course, are different from each other. And we might know the velocity, let's say at the perigee, and we're looking for a velocity at apogee. Okay, so that's the direction of motion counterclockwise. So again, what are the forces acting on the satellite? The only force acting on the satellite is really the gravitational, universal gravitational attraction, right? So here is the Earth, and let's say this is F sub g. That's the only force, and this is called a central force because it acts along the radial line, right? That's called a radial line joining from O. So if you attach our reference frame at the center where the Earth is located, then we can clearly see that some of the moment of the forces acting on the satellite is 0, because F sub g is actually along R direction. So R cross F is in this case 0. So which means that the angular momentum about O would be constant. And that means that R cross mv would be constant, because that's how we define the angular momentum. And that means because R and V are perpendicular to each other, this is the radial direction, this is the velocity direction, that means simply R times V times velocity is constant, right? That means R sub P times velocity sub P, which is the velocity of the perigee, is equal to distance at A at apogee times velocity at A, and that gives you directly RP over RA times velocity of P. So if you know the distance and the velocity at one point, and you know the distance at other point, you can compute the velocities as well. Now what would be interesting to ask is, if let's say you know the distance and the velocity at one position, and you're looking for the velocity and distance at another position. So in other words, we are going to be looking for, let's say, both RA and VA. In this problem, we assume that RA was known, but what if you're interested in finding RA as well? How would you solve this problem? Well, in that case, if you look at these forces, this force, the only force over here is really the universal gravitational attraction. It's a conservative force, okay, which means that you can apply conservation of mechanical energy equation. As long as you know what is the corresponding potential energy function for this universal gravitational attraction force, you can apply conservation of mechanical energy principle in conjunction with the principle of conservation of angular momentum to solve for both VA and RA.